Okay, let's begin. Thanks for joining. This is my first masterclass session with you. So excited to take you through something called GAMS. Welcome. I hope the course is going well and you're enjoying it and you're enjoying what you're learning. So let's begin. I know it's late for a lot of you. So I will start by taking you through GAMS today. All right, so I'm just gonna switch my camera off and then share my screen instead. Yeah. Okay. All right. So just let me know if you don't see my screen. Right now, I'm sharing a little plot with you to kind of take you through what GAMS is all about and what you're trying to achieve with this. All right. But if you can't see what I'm sharing, please just let me know. So what we have here on this graph is on the x-axis, on the horizontal axis, you have time. Okay, so as time progresses from 0 all the way to 12, so say 12 hours, there's an acceleration of some object. It could be a car, could be something, we don't really care. All we know is that this object accelerates accordingly as time goes by. So I think someone else got, yeah. Please just keep your mic on mute unless you want to ask a question. So please, if you want to ask a question, by all means, unmute. Feel like there's some noise in the background. Okay, all right, so let's come back to the whiteboard. So far, the whole objective of supervised learning, right, that you've been doing in this course is what you're trying to ultimately do is you're trying to predict your y given, your x variable, your independent variable. So in this example, what you're actually trying to do is you're trying to use this time, which is your x here, okay, and you're trying to create some sort of model that can predict and forecast this behavior, basically model these blue dots. All right, so you want a line to kind of try and put these blue dots. Now, what you've done so far is you've done linear models. So the generalized linear model. Now, the generalized linear model, it works well when the data is kind of following a straight line. But as you can see from this data, it doesn't really follow that shape. And that creates some complexity where linear models fail. So if you had to put a straight line, and I'm just doing this by eye, it'll kind of look like that, which isn't great because it doesn't capture the behavior that you want. Okay, it's missing a lot of the behavior here and here, and you can see there's quite a big gap here between the data, the actual data, the blue dots, and the green line, and we don't want that. So that's where GAMS has an advantage. Okay, so I'm just going to clear this, and I'm going to take you through what GAMS is trying to actually do. Now, GAMS would ideally create a model that will fit the data like this. So if I kind of draw it as best as I can, it'll kind of follow this kind of shape. Like that. And that's a pretty good fit. If you just look at it by eye, the GAM model looks pretty good to capture the overall trend. Now, what stops you from actually creating a model that actually tries to fit everything? And by now, I think you would have come across overfitting. So you could try and create a model that, it almost tries to connect every single dot like this. And yeah, it does capture the trend, but it's trying to capture every single data point. And that's just trying to capture the noise. You're not trying to capture that. So the red line is an example of overfitting. And what we're trying to get is the green line. The green line is what we're trying to get. Could you please, just mute if you're not, thank you. All right, great. So we're trying to create this green line. And now what I'm going to do is I'm going to talk you through the steps of actually what's involved in actually finding that green line. So I'm going to clear this and I'll take you through it step by step. All right. So first thing, what you're trying to do is you're trying to partition this data into quadrants. All right. So the first step is, remember, this whole objective now is you're trying to get that green line. So let's partition this data. And what do I mean by partition? Well, let's just break it up into quadrants. Okay, so the first quadrant, we'll make it here. This next quadrant is going to be here. And we'll have one more quadrant here. What you've basically done is you kind of split it into like equal parts. Right now, you may ask, okay, how do you know where to draw these black lines and where do you partition them? Some of you may have heard something of a term called percentiles, okay, or quartiles. Quartiles are just a specific type of percentiles. And what you're trying to do with the percentiles is all you're doing is you're splitting the data into equal percentages. What do I mean by percentages? Well, what we want is in the first black line between the boundary, which is here and here, we want to capture maybe 25% of the data. We want 25% of our volume of our blue dots to be there. And in the next one, we want another 25%. Okay, and then another 25%. And then the last 25%. All of it makes up 100%. Sorry, this should be 25%. So often percentiles are used, by default, but you can change it. All right. So that's one way of actually partitioning the data. Okay. The next thing we're going to do is we're going to create something called knots. So NKNOTS. I'm not known for my spelling, so please bear with me. So at each of these quadrants, we're creating a knot, like here. That and like that. So what you're trying to do is in each of these regions, you're going to create a function. So what you want to do is for the first region, I'll call this 1 here, this region here, but we'll just focus on this and we'll ignore everything after that. We're going to ignore all of that. All right. So if you focus. Okay, so if you focus on that first region, what we can do is we can try and just create one function, and it could be a line. Okay, it could just be we're fitting a straight line here. So like that, straight line. And the next part, maybe we can fit a curve. So we can fit a curve like this. And in the next part, we can fit another curve. And then lastly, here, you can create one more curve or straight line. Doesn't matter. But the idea what I'm trying to convey is you can break these up into different parts, each of them being a function, and then you can add them up. So in the first part, you would have this function here. All right. You would add that function. Let's call it B1. All right. You can call it whatever you want. I'm just going to call it B1. The reason why I use B is because it has a specific name that's pertaining to the letter B. And the next, this function here, we'll call it B2, then B3, and then B4. All right. So B1, if you look at just B1, what it actually is, if you look at this entire domain of X or region, All right. What B1 is, it's telling you that it's a straight line all until this point here. And everywhere else, it'll just be 0. It'll just be nothing, basically. That'll be B1. B2, on the other hand, here, this will be a curve like this, like that. And everywhere else, it's going to be 0. And here, etc., etc. And B3 and B4. And then what you do is you add them up. And when you add them up, it'll give you one specific shape. So let me erase this. So when you add it all up, it would give you one specific shape. Now, if you recall what I said for B1 and B2, it'll be like a straight line here. Then it'll be like a upward. Sorry, my bad. I think it was a straight line here, and here, and then a curve here, and then a curve there. Something like that. Now, it isn't exactly the green line, but the green line that I showed you earlier, but it's the concept that I'm trying to explain. I use the straight line for the first part. However, you're not restricted to using a straight line here. It could also be a curved line, like that. And that's how you end up getting the green line. And how you're doing it is you adding up these functions based on knots. Now, those functions that I spoke about, the B1, the B2, and the B4, those are called basis functions. It's just terminology. So if you hear it, now you know what I'm talking about. Oops, basis functions. Now, GAMS it's very effective because often in the real world, you can find data that actually behaves like this. It's not often that it follows a nice, clean, straight line. Often you can have data that follows wave-like patterns like this. An example, let's think about if you're looking at traffic flow in a certain city, right? As we know, if anyone of us drives somewhere in peak hour and then off-peak hour, let me clear all this up. All right, so let's draw the y-axis, and then we've got the x-axis. So on here on the x-axis, we have time of day. Let's say we start at 5 a.m. Instead of 0, we'll start at 5 a.m. Then we've got 6 a.m., 7 a.m., etc., all the way to like, let's say 7 p.m. And then here on the y-axis, you've got the volume of traffic. So as we all know, traffic is pretty light, but as we start approaching 6:30 or 7, traffic starts to go up like this, and then it starts dipping down again throughout the day. And then when it hits 5 p.m., it's going to go up again. It's going to go down again. Now I'm just stopping in one day. This time can go on for maybe a week. And if you had to do this for 1 week, you'll find that this pattern goes up and down again, up and down again. And linear models would fail to kind of model this. But GAMs can do pretty well at predicting this traffic. So this is an example where it comes in handy. And let me just check the chat if there's any questions. Or so far, so good. Okay, so let me just kind of summarize what I just spoke about here and the key points here. All right. So here, remember GAMs can capture, oops, I have no idea what happened there. Sorry, everyone. Okay, GAMs, or generalized additive models, can capture non-linear trends. And how does it go about doing this? It uses something called knots, right? It uses basis functions, right? And then it adds them up. adds them up to get the final model. All right. Now, the example I showed you a bit earlier, and I split it up into knots, and I split it up into 4 partitions. You could have the case where you're splitting it up into a lot more partitions like this. So you could have first partition here, then the next partition here, and here, etc., etc. So it could be a lot finer. And if you keep doing that, what's going to happen is you're going to have a lot of basis functions. Okay, so you're going to have a function here, 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 and you're just going to have a lot of them. And what happens is, because you got so many partitions or knots, you're going to overfit the data. You're trying to fit this too gradually, and that's that red curve that I showed you earlier. Okay, the one that just tried to fit everything. You recall that it went like, you're trying to fit every single thing like that. So when you have too many knots, you can overfit the data. Fortunately, when you're actually doing this with proper statistical and data
Like,
and heavy data analytics software like Python, it does a lot of this for you in the background. You don't really have to specify how many knots. It does that for you. Okay. But we're going to do this in Excel and I'm going to show you.
What's Excel?
Hi, Sir Daryl.
Hello.
How are you?
Good. How are you doing?
I'm good, thanks. No complaints, man. Just wanted to know about how does Excel work?
For GAMS?
Yeah,
or in general?
yeah.
Okay, we're going to get to that.
Okay, we're gonna go. Okay, no stress, no stress. I'm just gonna keep on listening, yeah, and engaging in the activity.
Sounds good. Susan, you have your hand up?
I just want to find out, since you said if we have too many knots, we'll end up overfitting our graph. So how do we know how many partitions we're supposed to have in order to actually have model like the green line that's not overfitted?
It's a good question. Okay, so fortunately, a lot of that work is done in the background of the statistical software. Like if you're doing it in R, for instance, or you're doing it in Python, you don't really have to specify that. Okay, you can just plug in the data and you can specify how you want to create the basis functions, which I'll get to in a second. But how many knots you want, the algorithm does do it for you. But let's just say, it couldn't do it for you. Then you, as the modeler, would have to do it by your discretion and by looking at it by eye. So this data set can be, let me just clear this out, right? Let's look at this data here. So by looking at it by eye, you can try and figure out, okay, where would one function fit a behavior appropriately? Like let's just look at this part here. This in black. Let's just look at this part here. I'll split it up here. Here, you can maybe tell, okay, there's one specific curve that can fit it like this. All right, but if I had to combine these two regions and make the partition here, I may not get one function that's going to fit it very nicely. Because as you can see, there's one function that can behave like this. If I use maybe x to some power, but you can see the behavior is going to change here. It's not going to follow a nice behavior. It's going to have to change and go this way. So it's probably best to split it separately here. But that's if your data is, you can see it by eye. This data is still a bit complicated to do it by eye. Something that's a bit easier to check by eye is maybe if you had a data set that followed something like this. Let's go. I could tell that my data kind of follows a straight line. Yeah. But then when I get to this point, it starts going down in a smooth curve like that. So maybe here to here, you want to split it, and you can tell that here a straight line is probably going to do a good job of fitting it, but here a quadratic maybe might do a better job. So you know to kind of just create one notch here and leave the boundaries as it is here. Visually, that's if you can see it. But just keep in mind, to explain this to you, I'm only using one X variable, one independent variable. In the real world, it's very seldom you're going to get just one X variable. So to visualize something in a higher dimensional space, it's not going to be easy, which is why those statistical software like R and Python will do it for you, fortunately for us. It has a way to actually do it in the background. Does that answer your question? Does that make sense?
Yes, but then, so what you're saying is that the event of us actually having to do it manually is rare because there are softwares for that, so we wouldn't have to worry about actually having to do the GAMS model ourselves.
Yeah, yes. So the idea of this lesson is to kind of understand, for you to understand how it works, how it goes about doing it, and what it can do.
Okay, thank you.
No worries. All right, so now let's move on to the Excel. All right, so I'm going to take you through a simple example.
Hi, Daryl. Sorry to
hello.
interject. I just wanted to ask, why do we do the GAM model?
Is that the question? Why GAM? Why do we
Yes.
even cover it?
Yes.
It's because it adds on to the GLM, the general linear regression model. So the general linear regression model is good, but it does very well when the data follows kind of a straight line kind of shape. But when you start getting curvature in your data, then GAMS is better.
Ah, okay. When do you know that you're supposed to do the GAM model? Or is it just a standard step that follows after the linear regression? Or is it specific to certain observations that you would have made?
What you're asking is actually, it is $1 million question in practice. You're asking, how do you know which model to use? And that's called model selection. And, to do it with the examples I'm showing you, just to kind of give you the idea, you can see how the data is shaped. But once you start increasing the number of X variables, it's hard for you to visualize it. So you can't really tell what the shape is in that high dimensional parameter space. I'm just showing you one X1. You start putting more X variables, X2, XT, you can't visualize it. So there's no way for you to actually determine how the data is shaped to even know whether it's linear or non-linear, is it curved, is it wavy? And so what you have to often do in practice is you actually have to try different models, but you need to know where is each model strong. So for instance, you need to know generalized linear models can work for linear data. So it's probably best to use that, okay, as one example in your, well, let's say in your pool of models. So you're going to try that. Then if you suspect maybe the data could be wave-like in shape, you don't know because you can't see it, but I'm going to put a model that can handle wave-like patterns. So I'll put GAMS in. Then it could be more non-linear shaped. So you're going to do this next week. But I'll just give you a glimpse of what you're going to experience. You could also have data. Yeah.
No, sorry, I'm listening. Yes.
Okay. So you could also have data that's not wave-like, but it's also not following a straight line. So the data could be like following like that, then like this, and like that, almost like stepwise, and just partition like that. So it's kind of irregular, but it's definitely not linear. And for this, trees can be effective. So when you're doing the model selection, you could add general linear model is one of the example, like linear regression. Then you could add GAMs, and then you can add trees. You can add much more models, but you need to know what kind of data each of these models can handle. And then once you implement those models, you want to see which one gives you the best predictions to what your actual values are. And that will determine which model you use. Does that answer your question? So beforehand, you won't really know which is the best model. You actually have to try them out. That will be your job as the model developer.
Okay, thank you.
You're welcome. All right, so let's get to Excel, and I'm going to take you through a simple example to illustrate how we will use GAMs. All right, so what we have here is your X and Y variable. What it represents doesn't really, it's not really important. Okay, so your independent variable is 1, 2, 3, it goes all the way to 20. And then we got a Y value, that your dependent variable mapped for each of these X values. So if I had to draw it or put it on a graph, it'll be the blue dots. Okay, so I'm just going to change these. I'm going to move the yellow dots so you can just see them, right? So just give me a second. I'm going to just change it. Okay, so the blue dots is what I want to draw your attention to. The blue dots, it's your actual Y values, the true values, and it's plotted against your X values, right? So it follows this nice parabola shape here. Now, what we're going to do is we are going to use GAMs to fit our model to this data. Now, some of you may see this and say, why do we even need GAMs? Because you can clearly see this follows a simple equation. Like if I had to do add a trend line here, and let's make it nonlinear. Let's make it a power law. No, polynomial. There we go. You can just put a quadratic polynomial and you can see it'll fit it, the dash line, right? So we don't really need GAMs. We could just put an equation to it. But that's not the objective of this lesson. The reason is I want to show you how GAMs can be used to fit it. And I need to show you this simple example because for more complex data, it's kind of hard to do it on Excel. But you just need to understand how it works when you're trying to fit your actual data. So I'm just going to, I can remove this trend line. Okay, there we go. So what we want to do is we're going to create a model, and that model will be represented by these orange dots, and we want these orange dots to be quite close to these blue dots, because then it's going to do a good job of putting the data. So the first step is, okay, so this is our X and Y, so I'll highlight that in yellow. Okay, so you just know that that's our data. What we're going to do is we're going to create our first basis function. Okay, so this basis function, we want it to just be applicable for a certain part of this X. And here, what we've done is we've just split it into 3 equal parts, 10, 5, 10, 15, right? It's actually not even much of an educated guess. All it is you're just splitting it equally, okay? So we'll go 5, 10, 15, and everything after 15 will go all the way to the end, all right? So the first basis function, what we're trying to do here is what we're saying for this basis function, what I want it to be is just a straight line. So in other words, for everything from 5, all right, and below, I'll make it 0. Everything below 5. So wherever your X value is 5 and below. Okay, so here's our X values. Everything that's 5 and below, we'll just make it 0. But once it hits values after that, we're just going to make it a straight line. So in other words, just make it X. And you can see, if you follow this formula, what we're doing here is we're just saying take the max of 0 or the time X, okay, 6 minus that 5. In the next row, it's going to follow the same thing. We're going to take the maximum of either 0 or just 7 minus the 5. And the next one, it'll be 8 minus 5, 9 minus 5, etc. So this is just a straight line. This is just like y equals mx plus c. This is a straight line. This is your B1. Okay. So in other words, everything from 5 onwards, okay, will just be a straight line. Below that, we'll just make it 0. Okay. Then next is our next basis function. This is 2. Now, this basis function is not going to be linear. So if I look at the formula here, it follows the same thing as what's happening with basis 1, but you'll see there's an exponent here. So what I'm doing is I'm taking the same values that I would have for basis 1, but I'm raising it to the power 2. But there's a catch. For this basis function, it's going to be a specialist from 10 onwards. So anything before 10, it's going to be 0. So I'm just going to go back to my whiteboard to kind of show you what I'm trying to convey here between these 3 basis functions, right? Because maybe it might not be great to see in Excel, but I'll just show you what it's trying to do, and I'll come back to the formulas. So here, okay, so what you want to do is, so I'm going to clear this and just give me some space on this board. Okay, so in your first quadrant, let's look at just B1, the first basis function. All right, so that first basis function, it works all the way up till as soon as you hit 5 on the x-axis. It's 0 all the way here. We're just talking about B1 now, the first basis function. It's 0 all the way here, but once it hits 5, it just becomes a straight line. Okay, all the way to the end. For the next basis function, B2, this function, all the way to 10, all right, it will be 0. So this is B2 now. All the way to 10, it'll be 0. But once it hits 10, it becomes a quadratic. That means it's proportional to x to the power 2. And here, it's pretty much just x straight line. So if you come back to the Excel, that's what we're saying here. In these first 2 columns, that's what we're saying. B1 is just a straight line as soon as you hit about 5. And for B2, as soon as you go about 10, it becomes a quadratic. All right, so that's your B2. B3 will be the same thing, but as soon as you hit 50, as soon as you go above 15, you're not just going to raise it to power 2, you're raising it to power 3. So in other words, you can think of B1, you're raising it to a power 1, B2, you're raising it to a power 2, and B3, you're raising it to a power 3. So that's your 3 basis functions that you've created. And now your predicted value is basically these 3 added up, but just like in your regression model. So I'm going to come back to my whiteboard here. If you recall, in your regression model, you had your predicted value. It's equal to your intercept, B0, plus your first coefficient, B1 times x1, all right? Let's just keep it as one variable. Keep it simple. Don't make x2. Keep it here, B0 and B1. Write this better. Not happy with the way this is done. Okay, we got beta 1 plus x. Now with the generalized, the GAMs, you're going to have the same thing. You're going to have a predicted y, right? You're going to have an intercept, but you're adding up these 3 models. So you're going to add up B1 times your x, and you're also going to add up your B2 times your x, and your B3. So each of them have their own coefficients. Each of them have their own coefficients. We can call it whatever we want, B1, beta 2, beta 3. All right. So you can add a further level of adjustment to it by giving it coefficients. So if I come back to the Excel, if you look at my predicted value, I'm going to double click here. What it's doing is it's saying these coefficients. Let me just create some space here. Hold on. You can see it better. what it's doing is it's saying each of the B1 has a coefficient 5.23, basis 2 has a coefficient 1.1, and basis 3 has its own coefficient, minus 0.019. And that first value, the 7.25, that's the intercept, your beta naught. And that's how you get your predicted value. So you multiply by the coefficients, and then you add it up. So the next line is the same thing. Your coefficients times their respective basis functions, and then we add the coefficient. That's how you get your predicted value. Okay, you do that for each one, and you get a predicted value. So that's your orange dots. But what we're trying to do is we want to know what should these coefficients be. So these, think of them as like tuning parameters. You can adjust them so that your model fits the data better. And what you're trying to say is, okay, how can I minimize my error or my SSE, the sum of squares of the error terms? Okay, how can you minimize this by adjusting these coefficients? What are the best coefficients that will minimize this? And you could do that in Excel just by using solver, right? So if you want to do it, you click on data, go to solver, and what you're trying to say is, I want to minimize L, or I want to minimize my SSE. So I'm going to select minimum, and I'm selecting L4. And how do I want to do it? By adjusting what? And that is by adjusting your coefficients, these terms, your I2 all the way to I5. I want to do it by adjusting those coefficients. You can use the GRG nonlinear method. You can just leave it. It should be pre-populated. You don't have to change it. But if you see there's something else, you can change to that. And then you click solve. And it does it for you. And it tells you these are the best coefficients because it minimizes that SSE to this value. Now look at the orange dots. They fit the blue dots. So in other words, your model does provide a very good fit to your actual data. So that's how GAMS works. Okay, you create basis functions, right? Each of these basis functions have their own coefficient, and it'll have an intercept. And what you can do is it tweaks the model. You can tweak these coefficients so that it would fit your, so that the final prediction will be as close as possible to your actual value. So let me just go back to the chat. Are there any questions? Did that make sense? Was there anything unclear there? Oh, I appreciate good questions tonight. Really very good questions. And I'm liking the feedback. All right. So now what I'm going to do is that first problem I showed you, this data, this is quite complicated data. All right. To do this in Excel, Excel doesn't do a really good job of doing it. So the method I show you, it's very simplistic. When data starts getting more complicated, the way you do your basis functions can become, you should use more complicated basis functions in order to fit more complicated data. So these basis functions, they're very simple basis functions. I think they're called hinge functions. The name isn't important, but they're very a simple example. But when you start using packages like R and Python and R don't use these type of basis functions. They use a bit more complex functions called splines. They're difficult to explain on Excel. The math is a bit more intensive, but all you need to know is that it does use a method called splines, and that the horsework is actually done in the background. And maybe if you want, I can kind of put something together, but it'll be quite intensive mathematics to explain how these spline methods work. But I'll just show you now how effective it can be. All right, so this example that I showed you is quite a simple example. But when you started off, you recall our data. Where's my data? Where is my data? I had it plotted somewhere. Second. Okay, that's the plot I'm trying to show in my Excel, if I can find it. I think it disappeared. What the heck is going on in my Excel? All right. Okay, so on the right, this graph, right? This is your, what I'm showing here, the blue dots, this is your actual data, what I started the lesson off with the whiteboard. So there's your column A, that's your X, that's your time, and in column B, that's the acceleration. So your actual data is shown by these blue dots. Okay. Now to do this, to put this in Excel, Excel wouldn't do a really good job. The orange line that you're seeing here, this is pretty much Excel's best attempt at trying to do it. However, R does a pretty good job of fitting it. And I know I had that plot somewhere. Where is it? Give me a second. Okay, I'll overplot it. Let's see if I can overplot it. Okay, so here, all my plots are just coming in stages. Let's add the R prediction. With me. Add. This is when you run it through R, and you'll get to this next semester. Exciting stuff. Let's say it. Please work. There we go. There's the green line. So R does it a lot better. And that's because R uses splines, okay, to create your basis functions. Splines is a lot more effective. It's actually the gold standard in these algorithms for whenever you use packages in Python and R, which obviously we're not going to do now, it's going to be next semester. The default method to create those basis functions is splines. But in Excel, we used hinge functions. They're much simpler and they work a lot better on simple data, like the one we just did here. But when the data gets complex like this, then you've got to use more complex methods to create your basis functions. So that is GAMS. It solves for nonlinearity, really useful in wave-like patterns of data. Any questions so far? Good.
Hi,
Yes.
I wrote a question in the chat, but I'll ask it anyway. Is the basic premise of GAMS making a straight line fit the curvature of the data by adjusting the gradient of the straight line that we would get during our linear regression by adjusting the gradient along the line of the straight line that we would get in a linear regression. I don't know if what I'm saying is making sense, but what I'm thinking is the straight line is straight, but in GAMS, what we're basically doing is we're taking that straight line and we're making it fit the curvature by adjusting the gradient here and then increasing it and making it fit the gradient of the data. Am I correct with that assumption?
Okay, no, I could see the confusion in it. Okay, all right. So remember, if you let me just share the whiteboard. Let's see. Clear this. Good question, and I can completely get the confusion. Let's just take a small region, and we'll put some data here. I'm going to put some. Let's put some blue dots here. Let's say our data is represented by these blue dots. Okay, and that's just this region, but here it follows a different shape. Now, the question you asked about adjusting the gradient. If you're fitting a straight line, okay, it'll probably do well in this region here. So here, adjusting the gradient would matter because you don't want the line to be pointing that direction. Let me choose a different color here. I'm using too much blue. Let's use red. So here, you'd want to adjust the gradient because it matters for the straight line. Okay, so the gradient matters here, but when you come to here, the gradient isn't going to help because it's not straight. Here, it's more curved. So it's more, you actually want to change the function. So here, in this region, you're going to have a straight line, y equals mx plus c. And the gradient here might matter. But here, the gradient isn't so important. Here, it's actually the function. Here, the function you probably want to use is y equals square root of x or something. So it's actually a completely different function. And GAMS looks at a couple of things. It looks at what function in each region would do well and what would be their parameters. In other words, slope and intercept. But often GAMS doesn't just use straight lines. It uses something called splines, which isn't really a straight line that has gradients. It's a function that's actually not linear, not a straight line. Does that answer your question?
Yes, I'm answered.
Good question. Tembeka?
Hi, thank you. Can you please go back to the example? I do follow and I understand what you're doing, but there's this part when you apply the coefficients to the calculation. I just don't get it. I guess maybe I'm just struggling to link it to the data that we have. That's why, because I'm thinking you only have basically two variables, but you then have about 3 or 4.
Yes.
Coefficients, and that's the part that I'm missing. But the other things, they make sense. I follow exactly what's happening. I'm just failing to link that part to the whole thing.
Okay. I see. All right. So we'll go back to the simple one, right? Okay. So you started off with just these two variables, right? Your x and your y. And so what you end up doing is you create these 3 columns, and I know it seems like you're creating 3 more variables, but you're actually not creating 3 more variables. You're creating 3 more functions that is based on the same x variable. So if you look at basis 1, if I double click on it, the only value it's using is the x value. And I'm using this red point to basically say, I want this function to only work within this region of x, okay? The next function, you'll see it's just a function of x again. It's taking the x value and it's also based on which region I want this basis function to matter. So in other words, think of the basis function as this B1, basis 1. It's a specialist for 5 and 10. It might be just good at 5 and 10. It'll do a good job, between 0 and 10. This function would be quite a good specialist between 0 and 10. But after that, it does really bad at it. But B2 is a specialist for the region 10 to 15, maybe. And then the last one is a specialist in 15 all the way to the end. So you haven't increased the variables. What you have is you've created 3 functions based on the same x or independent variable. And now the adding up part is, okay, how do we use these functions to get a prediction? So what you're doing is, right, you're creating a linear equation. Let me get to the whiteboard and I'll probably do a better job at that and I'll come back to the Excel. So here, what I'm trying to do is go back to my black line. Okay, I'll call my prediction y hat. So this is my prediction. And it's equal to y hat. And what the equation of that y hat is I'm going to create an intercept. I'll just write the full word, right? Intercept. So it'll be an intercept plus my B1. So that first column, if I come back to the Excel, let's just draw your attention to B1, basis 1. right? So I'm just talking about that. I'll come back to here. It's going to be my B1, but times some coefficient, beta naught. Okay, you can call it what you want. I'm just going to call it beta naught because that's what it's written in the literature. Let me write this a bit neater. Okay, so it's beta 1 times beta naught. And I'll explain exactly what this beta naught does, right? So your B1, it'll give you a value in the region of your X. So say here, your B1, let's say your B1 is based on this region here, okay? Now it'll give you a value, say the line is probably like, yeah, like say it creates a function like this. What that beta naught does, right? Let me change it. I don't call it beta, let me call it beta 1, sorry. What this beta 1 does, it tells you whether to shift it up or to shift it down. So if the beta 1 is positive, it's telling you move it up. If it's negative, it's telling you go down, move it down. That's what it does. It scales it. All right. So in the same way, you're going to have beta 2, so B2, your base is 2 in this region. So you're going to add this part here, B2 times its own coefficient, beta 2. And this B2, it could be a function like this. But what the beta 2 tells you is shift it. Right? You multiply it by a factor. And so that, if you come back to here, that's what you're doing here. Each of these columns is scaled by a coefficient. So this, let me write it here. That's why maybe this might be confusing. This is beta naught. This is your intercept or intercept. This is your beta 1. This is your beta 2 and beta 3. So beta 1 is multiplied by your this column. So we multiply everything in your first basis function by your beta 1. Everything in basis 2 is multiplied by beta 2. Everything in beta 3 is multiplied by this coefficient. So if I click on the predicted value, you see that's what you're doing. It's saying basis 1 times beta 1 column, the 9.818, beta 2 value, basis 2 value times the 1.32 plus basis 3 times your 0.019, and then plus your intercept, the blue square. And that's your predicted value. So it's the same thing what I'm writing out here. Okay, so if I complete this for the last basis function, it'll be plus B3 times the coefficient for that. And if you do that, for each row, you're going to get a prediction for each row. And that's how you get your predicted value column. That's what it is. Think of these
So the
coefficients
bases 1, 2, 3, those are your independent variables.
They're functions of the independent variable.
Okay, fine. I think, okay, I get it. I follow now.
Right.
I thought
Good
it was independent of what was happening with the coefficient, the coefficient values. But now I see that it's actually a value. These coefficients are as a result of these values. The variables bases 1, 2, 3.
Yes. Good
Okay,
question.
cool. Thanks.
No worries. Okay, let me come back to good questions, everyone. Panda?
Hi, Daryl. I just sort
Hello.
of ask, in the example started, you sort of had like examples of the coefficients, and then you use the solver to find like the right ones. So I wanted to ask, like, if we just have the data, then how do we find the coefficients? Is they like a data, can we use the data analysis tool, or what do you think?
Yes. So if you have your data, right, these values may not be optimized at first. So you could just have them initialized at 7.2. It could be anything. I'm just making up numbers here. And then or 0.75. I'll leave the last one as is. So yeah, could be that, but it's not optimized. But you can initialize it to whatever you want, because ultimately you're going to use solver to solve what the SSE value is. Remember, the SSE value is simply, it is I'm sure you must have done it for general linear models, but anyway, you can just follow the formula here. Excel does it for you, okay? What you're trying to say is, what is the difference on average between my actual Y values and the predicted values? And I want that difference to be as small as possible, because what I'm trying to say is I want my predicted to overlap the actual values. And so how can I use solver to change this in order to minimize that? So when you start off, you can initialize it to whatever you want. Just a guideline, whenever you're doing the intercept, right? Even if you're doing for general linear models, GLMs, it's a nice guess to just use the average of whatever your Y value is. So in other words, look at what your Y value is, just take the average and place it there. But for everything else, you can just make it random and then use solver. Did that answer your question? Great. Cool. Some great questions today. Yeah, I'm hoping you liked this topic. These models are used. They become, if I believe your textbook is Elements of Statistical Analysis. I think it is that. But let me know otherwise. But the authors of that book are the ones that actually created this model. So just out of a point of interest. So yeah, that book obviously covers it in quite detail. Is the basis? Okay, yeah, the same question you asked. One more thing I'll just cover before I close off. There's a, let me clear this board here. Remember when I started, I said, if you choose a lot of knots, you could end up overfitting. Okay, you could start trying to fit every single data point, and that's just because you choose a lot of knots. There's a parameter used in GAMS called the lambda parameter, and that just controls the wiggliness. You don't have to worry about setting it, because often that is just set in the algorithm in R and Python. In the Excel, in the hinge functions we use, lambda doesn't come into play. But whenever you start using splines in R and Python, which you'll do next semester, this lambda parameter comes into play. All you need to know for what lambda is you can think of it as a penalty parameter. Okay. When lambda is close to 0, then you're going to get this red wiggliness. You're going to get the zigzag. You're going to get overfitting. Okay. But when lambda is large, right? When you increase it close to infinity, as it approaches infinity or high values, then it can become a straight line. So it's too rigid. So what you're trying to do is you're trying to find a middle ground for lambda. Okay, somewhere in between this is the sweet spot where you're going to get the green line. You're going to get the green line for a perfect lambda value like that. That will give you the green line. But what I just want you to take away from this is that all you need to know is as lambda goes towards 0, or as you make it as small as possible, it'll overfit or you'll get more wiggliness. But as you push it to a higher value, that wiggliness changes to a straight line, becomes rigid. So you could underfit here, and you can overfit here. All right, that's what I want to take away from that. Yes, yes, Andrew. It is very similar. Good analogy. it is like that. It's a penalty parameter. All right. I enjoyed the session. I hope you did, and I really hope you followed. But even if you were struggling, please drop me an email. Let me know if you have any questions, anything you want me to cover specifically on this. Happy to help. So next week, I believe you're going to do trees, and Gareth will take you for that. Exciting stuff. All right, I will make the recording available, and thank you very much for. Oh, let me put it in the chat. Let me stop sharing. I'll put my email in the chat just in case. If you want to drop off, you can, but my email address will still be there. Just give me a second. Email address is here. No problem. I think we've got most of the material, or pretty much all the material loaded on Arc. Michelle, I will do that. Yeah, I'll upload the material on Arc. I'll make the recording available and the Excel I shared with you. No problem. All right, everyone. Thank you for joining, and have a good evening. We will chat soon.
Thank you. Bye.